Let's talk lesson 12. As I mentioned, we are going to take 2 days to do lesson 12. I don't know. I have tried over the years to squeeze it into 1 day, and I've given up trying. That's what it comes down to. I don't even bother trying anymore because it's just not easily possible. So, okay, we did calculus yesterday. Now we're back to review today. Okay. We are a whole bunch of identities, okay, and then some graphs. So, looking at these identities, and again, it comes down to be familiar with them. Are there ones that might pop up that you need to know on occasion? Yes. Okay. Might they pop up in another problem? It is possible. So just, be familiar with them. Now, right here, they list 6. And it says, these following are the key trigonometric identities. Okay. Now, as you look at those 6, when it says in homework to write down these 6 key trig identities, because there are homework problems that say, if I recall, going forward, it says, write the 6 key trig identities. And then maybe I'll have you prove one or something. But this is what we're looking at, okay? So, the first one, you know that one, right? That's a piece of cake. Sine squared x plus cosine squared x equals 1. So that is one of our Pythagorean identities. Tangent x equals sine x over cosine x. I guess that's officially, I don't even remember what they call them. I don't know, it's definition of tangent. I can't remember what that column was called, but you guys know tangent. And then these 4 all fall together under the sum and difference identities. Okay, so know how they go. When you have sine, it's always sine, cosine, and then cosine, sine. And the addition subtraction sign matches, right? So if it's sine of 2 items being added, then we'll say sine, cosine, sine of the first, cosine of the second, plus cosine of the first, sine of the second. Okay? And we use this, for instance, if we can't use a calculator and we have a situation where, okay, we want to know, trying to think of one we often did. Like if we're doing 15. 15 degrees is not one that's on our chart, right? But 45 and 30 are on our chart. And 45 minus 30 is 15. So this is a situation we use these. On the sign of 2 items subtracted, the only thing that changes is that since it's subtraction, we're subtraction. Now remember the cosines. It's cosine, cosine minus sine, sine. Remember your adding, subtracting sign is the opposite sign. You guys have your ways that you remember those? Or hopefully they'll come back to you. I don't know how much you remember them right now.
I remember doing stuff.
Yeah, they're not too hard to use. They really aren't. So the tangent one was a fraction one, if you recall. Or at least I think. Yeah, because it was like 1.
Sine squared. Oh, it's actually easy.
Or maybe it was tangent of A minus tangent of B over 1 plus tangent A times tangent B or something. That's how bad it is. I can't remember the tangent one off the top of my head. So, but that just goes to show you these are the more. Yeah, know that one, right? Okay, so let's look at some of these. Here we have a simplified sine of theta plus pi over 4. And based on the directions, we are using some of our key trig identities to do this. Which identity can we use with sine of theta plus pi over 4 to write this out in a different format?
It would be the sine s plus t, right?
Yep. We're going to use this top one, right? This top adding, subtracting one right there. So, sine of s plus t starts off sine s cosine t. So in this problem, it's going to be sine theta cosine pi over 4. It's the sine identity, so the adding, subtracting sign stays the same. And then it's cosine s sine t, which in our case is going to be cosine theta sine pi over 4. What do you know off the top of your head there? Or what are you supposed to know off the top of your head?
But let me draw my triangle.
Okay, yeah. You should know cosine of pi over 4 and sine of pi over 4. Or you can figure them out with little effort, if that's the stage we're at. Sine theta and cosine theta. Theta is a variable, right? So that's just staying. So sine theta, cosine of pi over 4, square root of 2 over 2, plus cosine theta, and sine of pi over 4 is square root of 2 over 2. Now, I tend to write them as square root of 2 over 2. You realize equivalent to that, though, is 1 over square root of 2. That is equivalent. And in random situations, it is more beneficial for it to be unrationalized. But the only other thing we can really do to clean this up, what do you notice about both pieces now? Yeah. So how I have this written is factor out the square root of 2 over 2 out front. And then that leaves that we can put in parentheses sine theta plus cosine theta. Okay. I didn't mean to do it earlier, but example 2 I kind of already threw out how we would do that. This falls into that category of I didn't really look ahead at these notes because I just, go with them. Okay. Find the exact value. What do I mean by exact? Don't use your calculator. I don't want a decimal answer. I want what you can get with your pencil and your brain. Okay? So an exact value, in other words, if there's square roots in the answer that would be decimals normally, we leave them as square roots, things like that. So what do you know about cosine of 15 degrees? Okay, one option is we can change 15 degrees into 45 degrees minus 30 degrees. Now, if you prefer, you could also use 60 minus 45. And it would work out the same in the end. Okay, so cosine of 45 minus 30, I'm going to rewrite this. How does a cosine identity work? I'll agree with cosine, cosine. So cosine 45 degrees, cosine 30 degrees, and that's opposite the sine, so plus sine 45 degrees, sine of 30 degrees. And this is where Frost drew his triangles out earlier. He's going to use them again. Okay. Again, it's however you guys remember these. But you saw a little bit of on the last test, didn't you? And I know you guys haven't seen those tests yet, but there were a few people that messed up the answer because of they messed the value up. I don't even remember what you had to find there, but I just remember seeing, oops, and I don't remember who it was at this point, but I saw that happen a couple of times. Okay, cosine of 45. It's the same thing as pi over 4 from above, isn't it? Square root of 2 over 2. Cosine of 30. It is. That's one I have to think harder about, so I had to pause and think on that one ahead of time. Sine of 45. Square root of 2 over 2. Sine of 30. 1 over 2. Now, if you recall, we do want to clean this up, so I can multiply. Square root of 2 over 2 times square root of 3 over 2 is going to be square root of 6 over 4. Square root of 2 over 2 times 1 over 2. Square root of 2 over 4. And then traditionally we were expressing these as one fraction. So square root of 6 over 4 plus square root of 2 over 4 is going to be, no. Square root of 6 plus square root of 2 all over 4. Okay. Radicals, we can multiply as long as they're both square roots or, the same type of root. You can multiply any radicals you want, assuming they're the same type of roots. adding, they have to be exactly alike. Okay? And then when we're multiplying fractions, remember you just multiply top times top, bottom times bottom. And thus my denominators are 4. I know the square roots throw us off there. So, okay. We mentioned tangent at the top. Here it says develop an identity for tangent of a plus b. So what we're going to do here is we are going to get to what you guys know, the one we talked about that was like the tangent plus tangent and 1 plus or minus tangent tangent. Like I remember it's something like that in my head. Okay? We're going to develop that. Means we're going to kind of do a proof of it. Okay? And show how we can get from what we have at the top of the page over to what the tangent identity is. Does that make sense? So, we are starting with tangent of A plus tangent of B, right? Or tangent of, A plus B. Now, what do you know about tangent based on those 6 identities up above? It's sine over cosine. So if tangent is sine over cosine, then tangent of A plus B is sine of A plus B over cosine of A plus B. Now, again, using our identities from up above.
Shayla Clowers-Myers, please report to the middle school office. Shayla Clowers-Myers.
Okay, so what do we know from up above again? Sine of A plus B?
Is sine of A times sine of B plus cosine of A times sine of B.
It didn't come out exactly right,
Yes,
but
sine of A times cosine of A plus cosine of A or cosine of A.
you got the different part out this time.
Okay, I'm writing it correct. I want you all to know that, but it's not coming up.
And in all honesty, I can write it better than I can say it too. Just because I have to process too hard. Did I write it right? Sine A, cosine B plus cosine A, sine B. See, I can read it perfectly fine now that I have it written down. Okay. Cosine of A plus B. Okay. My denominator is cosine A, cosine B minus sine A, sine B. Okay. And I'm verifying against my old notes because I don't trust myself with all this. Okay, now, here's the deal, guys. We have to find a place to go now that gets us there. And we're kind of, it's more just doing math than not using the identities up above. And I don't have a good recommendation other than so we kind of talked about what we know the tangent one to be, right? Or kind of what I remember it to be. Which on top is you're either adding or subtracting the 2 tangents, right? On bottom, it's always 1, and then plus or minus the 2 tangents multiplied, right? So what is that first number always going to be on bottom? A 1. So as we look at this right here, eventually this is going to end up being a tangent plus or minus a tangent, and this is going to be 1 plus or minus a tangent, right? So what we're going to do, what I want to know is this first entry right here, cosine A, cosine B. How do I turn it into a 1? Mathematically speaking, what do I do to something to make it a 1?
Raise to the power of 0.
But if I raise everything to a power of 0 here,
Then
then everything's 1, and that doesn't help.
Okay, you divide it by itself.
Divide by itself. Okay, multiply by reciprocal. And I'm going to use divide by itself in this case just because I'm doing this with everything. So what I'm going to go through and write out is that we're going to divide this by cosine A, cosine B. Now, if I divide this by cosine A, cosine B, in order to keep this fraction equivalent and not change the value of the fraction, we're dividing everything on bottom by that and everything on top by that. So I'm going to write this out. And what I'm going to write out is, so on top we had sine A, cosine B. And what am I going to divide that term by? Cosine A, cosine B. And then plus the other piece of the numerator was cosine A, sine B. And what am I going to divide that by? Cosine A, cosine B. All over, so that's all the numerator, right? Denominator. I'm going to have cosine A, cosine B, and I'm going to divide it by itself. Cosine A, cosine B. Minus, and then I have sine A, sine B, and I'm going to divide it by cosine A, cosine B. Okay, did you guys get that all? If you want a side note to help you later about what the heck we just did and why we did it, I just wrote, we know that the first entry of the denominator is 1, and so we divided by cosine A, cosine B. Does that make sense there? Now, I can give you guys a moment if you need to write that down, but now we just have to finish it up. Okay, you ready? I'm going to do this piece by piece. First thing in the numerator. Sine A cosine B divided by cosine A cosine B. What do you notice?
There will be cosine A.
Where I'm at, cosine B's are going to cancel. So as I look at the first part there, cosine B's are going to cancel, yes? And what remains? It's sine A over cosine A, which is tangent A. So this is going to be tangent A. Plus, what about the second part of the numerator? Cosine A's cancel. What do you know about sine B over cosine B? Tangent B. You seen how this is coming along? Okay, denominator. What was the whole point about the first thing in the denominator? Everything cancels and it's 1. Minus, what about the second part of the denominator? Nothing cancels. Yeah, we're going to clean it up. Because I see a sine A over cosine A and a sine B over cosine B. Tan A, tan B. Because they're different tangents. Now, why did we have to develop that? The idea behind it is because we have a way that we can develop it, we don't have to have it memorized. Okay, that's the idea that I look at it as, is, okay, we have a way to develop this. We don't have to have it memorized because as long as I know my sine and cosines, you know, everything I did was either based on an identity up above or it was math. Okay, just basic math skills. With trig and extent, which made it weird, but, you know. So that's the idea behind why we developed it. Okay? Is it a good one to be familiar with and know some of the basics? It is, right? Questions on that? Okay. What about example 4?
Same sort of thing, but now the sign is minus.
Okay. Do I need to work it all the way through?
Hopefully not.
Okay. So if we were to start it, it's tangent of A, minus B. We know tangent would be sine over cosine, right? Now, we could way as above, it's just the signs are different, right? Do you guys want to jump and tell me what the answer you would expect it to be? Except you left out a sign on top. It was tan A plus tan B, now it's going to be tan A minus tan B. Okay, so if we were to work this out, we would end up with tan A minus tan B all over 1 plus tan A tan B. And however you memorize these, or be familiar with them, remember the top sign is the same as the problem. The bottom sign is opposite of the problem. Sound a little familiar? Okay. As we get ready to flip over to the other side, there are double angle identities listed at the bottom. Now, if you want to go back and fill in the work there, more power to you, but to me, it's repeating all the work. So, double angle identities. So, double angle identities are used when there is a 2 on the variable. So, if you recall, there is 1 for sine x, but there are 3 for cosine 2x, aren't there? So there's only 1 for the double angle sine 2x, but there are 3 different ways we can write the cosine 2x one. All just depends the situation. Do you need something with only sine, only cosine, or, they can use both. So go ahead, and we're going to kind of look at where they come from. And again, it's all about using those original 6 identities today, right? Where am I? Okay. We get them by doing the following. So basically, we're going to develop them. Okay, again, looking at how they connect. So we'll start with sine of 2x. And as we think about sine of 2x, and our identities from the front side, I'm going to take 2x and break it into x plus x. So then, if we say 2x is the same as x plus x, this is a sine of x plus x. And then we can use our addition identity, or sum identity, I guess, because it's sum and difference identities. So, with the sine identity, we say sine cosine. So sine x, cosine x, and then it's a plus, keep the same sign, and then cosine x, sine x is what we normally do. What about sine x, cosine x plus cosine x, sine x? What? We can add them? Are they like terms?
Yes.
Yeah. It's cosine sine, or excuse me, sine cosine, and the cosine sine can be flipped around to also be sine cosine. So sine cosine plus sine cosine is going to be how many? 2 sine cosines. So 2 sine x, cosine x. Hey, does that sound familiar? Yeah, according to the front page, the double angle identity for sine of 2x is 2 sine x cosine x. So again, the connection is if you know these other basic identities, you can develop all the others if you forget them. I'm not sure realistically if any of us are going to do that, but it's looking at the connections is what we're doing here. Okay? Now, that was sine of 2x. What else do we have to do? cosine of 2x. So what do we know about cosine of 2x? Cosine of x plus x. And so if we use our sum or difference identity, cosine of x plus x is going to be cosine x minus sine x. Okay, so cosine squared x minus sine squared x. Hey, guess what? That's one of them, isn't it? One of our options for cosine 2x is cosine squared x minus sine squared x, which reminds you of the Pythagorean identity, but it's not. Right? Pythagorean identity, they have to be added. Now, speaking of that Pythagorean identity, there are two other ways to express this. And the two other ways we can express this cosine squared x minus sine squared x are to use that main Pythagorean identity to rewrite them. So for instance, how could I rewrite cosine squared x?
Sine squared x minus 1. Or no, 1 minus sine squared x. Right?
Yeah. 1 minus sine squared x. So if I take this and I rewrite cosine squared x as 1 minus sine squared x, and there's already a minus sine squared x. What's 1 minus sine squared x minus sine squared x? 1 minus 2 sine squared x. Hey, guess what? That's a thing. That's another one of our ways to write this double angle identity. Okay? Can you guess how to do the other one?
Do the same thing, but with cosine. Or with sine.
Yeah. So if you go back and use that cosine squared x minus sine squared x, this time we'll keep the cosine squared x minus, and we'll replace sine squared x with 1 minus cosine squared x. And so what is cosine squared x minus the quantity 1 minus cosine squared x?
Cosine squared x minus 1. Oh, yeah, 2 times 3x.
You'd end up with cosine squared x minus negative cosine squared x, so plus, so it's going to be 2 cosine squared x and then minus 1. Okay, and honestly, that's one of those things. For cosine 2x, when I'm, in calculus or pre-calculus, I'm working with my double angles. I can remember cosine 2x is cosine squared x minus sine squared x. I can remember that one. I tend to get the other one too confused. One of them's 1 minus, the other one's minus 1. If you know this first one, though, you could convert to either of the other ones using that Pythagorean identity. Okay? Now, do we remember the one for the double angle for tangent?
No, but I have a feeling we're going to find out.
Well, yeah. I'll be honest, I don't know if I would remember this one without just glancing at it now, so. No. Okay. Tangent of 2a. What do you know about 2a? It's a plus a. So tangent of a plus a. Do we have an identity that can help us with tangent of a plus a? We could, but I think that'd be more complicated. Instead of going for the originals, I was going to use the one we developed. as opposed to going back to one of the originals. Now, I'm trying to think, how difficult would it be to go sine over cosine? I think we ended up doubling back to do some of our work from earlier is what we'd end up doing. So we could do it, but we'd just be redoing work from earlier. And if you think about it, where did we end up? If it's tangent of two items added together, the top is, right, tangent A plus tangent A. 1 minus tangent A, tangent A. And so if we clean this up, what is tangent A plus tangent A? 2 tangent A. What is 1 minus tangent A, tangent A? Yeah, 1 minus tangent squared A. So that is our identity for the double angle of tangent. Okay. And I will say the good news about calculus, these don't come up a whole lot. Okay, randomly when we're dealing with things they might, but this is not going to be part of our everyday math here. This is just, we need to review a little bit of what you guys did last year, right? Okay, that was double angles. You ready for half angles? I kind of agree. Well, I mean, I guess I should say they're my least favorite to deal with. Like when teaching pre-cal, they're just my least favorite to deal with. But, okay, half angle identity. So a half angle identity is called that because it's the angle divided by 2. Okay, so that's why we're talking half angle identities. So the half angle identity for sine, plus or minus the square root of 1 minus cosine theta over 2. The half angle identity for cosine, plus or minus the square root of 1 plus cosine theta over 2. Trying to think, if you're remembering a different form, we sometimes had the square root and it'd be like 1/2 minus 1/2 cosine theta under the square root. I can't remember which way the pre-cal book does it, but okay. The double angle identities can be manipulated to find the half angle identities. So, debating where I want to start here. We'll start by trying to find the sine, the half angle sine identity. And in order to do that, we're going to use the double angle cosine identity that involves sine. So the double angle cosine identity, so cosine of 2x, and the one that involves sine is 1 minus sine squared x. Okay? So, if we're trying to manipulate this and get it to be sine of theta over 2, which we'll get there, okay? We're going to start off by solving this equation for sine. So, if I solve this for sine, if I add sine to the other side and subtract cosine 2x over, does that work for you guys? If I add sine squared over, I'm going to have positive sine squared x equals, we already have the 1, and now it's minus cosine of 2x. Glad I looked at my notes. I have a mistake. I didn't write down my identity right. Maybe I said it, but I definitely didn't write it down. That's supposed to be 1 minus 2 sine squared x, yes? Isn't that what it says up above? It's supposed to. I was supposed to be copying it down from up above. I feel like maybe I said it, just didn't write it. I don't know. But, okay. That was supposed to say cosine 2x equals 1 minus 2 sine squared x. Excuse me. So now I'm going to move over, add the 2 sine squared x over to the other side, and subtract the cosine 2x. Okay. Continuing along. How do I get sine by itself? Divide by 2. So then I'm going to have sine squared x. And I'm just going to do it as one big fraction because that's what you see up above. 1 minus cosine of 2x divided by 2. I saw it going out of the corner of my eye, but
So what happens?
my computer goes to sleep. I think there's a half-hour time limit on it. I don't know. If I'm thinking about it, I'll reach over and move the mouse at some point during the lesson. I wasn't thinking about it, you know. Unfortunately, more often than not, I don't think about it. So, computer go to sleep. I'll sometimes like, oh wait, I better move that one to make sure it doesn't fall asleep. But, okay. Now, as we work, we're trying to get this to be sine, right? And we're almost there. I think you know what other step we have to take, but we're going to do a step first. Because right now, if I work to get sine by itself, it's going to be sine of x. I need it to be sine of theta over 2 or something divided by 2, right? You know, if we're not worrying about what variable, I need it to be something divided by 2. And so what we're going to do is we're going to take this x right here, and we're going to say, let x equal theta over 2. And we're going to substitute in. Okay? And we can do that as long as every place we see an x, we substitute in. We can't just do it once. We have to do it every place. So if I go ahead and rewrite this, and I guess we could have waited till later, but I'd rather get it done now. Sine squared x. Instead of x, what am I replacing x with? Theta over 2. So it's sine squared of theta over 2 equals 1 minus cosine of 2 times x, except what is x? Theta over 2, and then all over 2. So I just took x and replaced it with theta over 2. Now, obviously, in the next step, what is 2 times theta over 2?
2 theta over 2.
Yeah, it's just going to end up being theta. How do I get sine by itself? Square root. Can I go ahead and do that at the same time? The square. Oh, you know what? Actually, I did go ahead and. Okay, I guess I did go ahead and write it out. Sorry. And then took the square root. So sine squared of theta over 2. And then it's 1 minus cosine of theta all over 2 is what I did. And then I took the square root. Square root of sine squared theta is, or sine squared theta over 2 is sine of theta over 2. What's the square root of 1 minus cosine theta over 2?
Square root of 1, or plus or minus square root of 1 minus cosine theta over 2.
Okay. Plus or minus the square root of 1 minus cosine theta over 2. That's a thing. There we go. That's Ross is saying. That's a thing. At least in this lesson, right?
I'll find ways to bring it back.
I'm not surprised. Now, I don't know, do you guys still have room over here? That was 1. Can we do the other similarly if I recall?
Seems like it.
Yeah. The other one's going to work out very similarly. The difference here up here at the top, it's cosine of 2x, and we're trying to get to cosine of theta over 2, so I'm going to use the one that involves cosine, which is 2 cosine squared x minus 1. I'm not going to forget my 2 this time. So if I'm trying to solve for cosine, honestly, I'm going to leave it where it is and add 1 to the other side. Although my brain, I'm going to flip-flop sides. So I'm going to say cosine squared x. Dang it. You knew what I left off. You knew to look. 2 cosine squared x equals cosine 2x plus 1. How do I get cosine squared x by itself? Now we'll divide that 2 away. So cosine squared x is cosine of 2x plus 1, all divided by 2. And if you look, this is the spot last time where, what did I do? Yeah, every time you see an x, we're going to replace it with theta over 2. So instead of cosine squared x, I'm going to see cosine squared theta over 2 equals, instead of cosine 2x, I'm going to say cosine of 2 times theta over 2 plus 1, all divided by 2. So then cosine squared of theta over 2 is equal to cosine of theta plus 1 divided by 2. And that last step is to square root. So cosine of theta over 2 is equal to plus or minus the square root of cosine theta plus 1 over 2. You realize it is a thing, right? Okay, cosine plus 1 is the same as 1 plus cosine, right? Okay, just making sure. Okay. Ready for example 6? If you keep in mind, all these identities were like an entire chapter last year. And we're doing them all in like one day. Okay, example 6. I kind of ran into example 6, but that's all right. Show that sine of x over sine of 2x equals secant x over 2 for all values of x that makes sense. So I just wrote sine of x over sine of 2x equals, because we're just going to work with the left side and eventually arrive at the right side. Thoughts there?
So the sine of x was the same, but sine of 2x equals 2 sine x times cosine.
Yeah, can we use the double angle identity for sine x, or for sine 2x? Yep, I'll leave sine x the same. I can handle that. Double angle identity says sine 2x is 2 sine x cosine x. And that's a random good one to know for that reason, for these substitution purposes, simplifying an answer. What do you notice?
There might be a
There might be a sign
sine.
that cancels. What am I left with then? 1 over 2 cosine x. Not quite. Yeah, the 2 is going to stay in the denominator, but cosine goes to the top as a secant. So secant x over 2. That would have been crazy challenging for you guys last year. Maybe it still is for some of you. I don't know. Then again, it's always easier when I'm leading you through it, right?
Yeah, ask us after homework.
Okay.
Maybe randomly go to logarithms.
Again, I feel like they're just trying to squeeze as much review as they can in, because it does kind of seem like we randomly go to logarithms. I'm wondering, is this a good stopping point?
Maybe because that might give us enough time to look at our test.
That's exactly what I was thinking, is I could let you guys take a glance at your test.
Or homework.
Yeah. So, and we can talk about homework tomorrow too. Okay. So let's pause here. We'll reconvene tomorrow, because as much as I would love to, I am not doing vlogs in like 10 minutes. I mean, you know, We've got there's 4 graphs there. I mean, it's like 9 graphs, really. And we got to pull it all back together. So, yeah, it's not happening. So, that's a good stopping place so that we don't stop awkwardly. And since you haven't seen your test,